A base unit is a defined amount. For example, someone decided that a particular distance was a good increment to measure with and defined that distance to be a meter. There is no other way to come up with a meter other than to go by the definition. A derived unit is some combination of base units. Speed has a derived unit of meter per second made up of the base units meter and second. It takes 7 base units to uniquely define a unit system. Do you know what each of these 7 symbols represent? There are many systems of units in use today. In this course, we will primarily focus on the SI system of units, also called the MKS system. In this system, 3 of the base units are length, meter, mass, kilogram, time, second. These are part of the fundamental 7 units that must be part of a unit system. Note that the MKS unit system is based upon these quantities first and foremost. The first fundamental unit is length. The following information is true about length. You can place any type of ruler on this page you would like. It can be a meter stick or a yardstick. You can also include an odometer, which measures length or distance in miles or kilometers. The tape measure that measures your waist, hips, chest, and height is also measuring a length. Remember, it is important to record the units when you make a measurement. The difference in a 36-inch and 36-centimeter waistline is more than you might think. The second fundamental unit is mass. The following information is true about mass. Please note that mass and weight are not the same thing. Mass is a fundamental unit and weight is a derived quantity. Hence, mass and weight are proportionate because of gravitational attraction, but mass is the fundamental quantity and an object's weight is derived by multiplying the mass by the gravitational acceleration constant. Weight equals mass times gravitational acceleration. This scale is reading your weight here on Earth. It reads pounds. If it were measuring your mass, it would read in the units of slug. Gravity makes all of the difference in measuring weight, while mass is a measurement of an object's inertial response or lack of movement. Mass is generally measured by comparing it to a known mass or a standard. A triple beam balance, such as this one shown, is most often the method of choice when measuring mass. If you are a farmer who is delivering your wheat to the local elevator for sale, what is the measuring device that is used to determine what amount of product you are selling is called? It is a scale which measures the weight of the commodity. The measurement is in pounds, which is usually converted to bushels. Even though the underworking of a scales house measures the mass of the truck and produce, the calibration of the scale gives a resulting value of pounds, not slugs. This is an example of a standard kilogram. This is the object at which all other masses are compared to. The third fundamental unit is time. Units of time, seconds, S in all 3 systems is the same. We have defined in terms of the oscillation of radiation from a cesium atom. How many ways do you know of to measure time? Nearly all quantities that we measure in physics have 2 properties: size or magnitude and a unit of measure. We can define 4 fundamental physical quantities: length, mass, time, and current. All other physical quantities can be written as combinations of 2 or more of these 4 basic physical quantities. In practice, 3 other physical quantities are defined: temperature, amount of a substance, and luminous intensity. The reason for defining these quantities as fundamental is that it is much more convenient to define them separately rather than to express them in terms of the basic 4. Having several different unit systems poses a major problem when people using 2 different unit systems try to communicate. So how do you get the correct 3-inch bolt for your Audi if the salesperson on the phone doesn't know what an inch is? The solution to this problem is the conversion factor. A conversion factor is a multiplier which has a value of 1 and is used to convert a quantity from one unit of measure into its equivalent in another unit of measure. How will we get this square peg to fit in the round hole? Here is a great technique to check the correctness of an equation. It is called dimensional analysis. Dimensions like length, mass, time, and combinations can be treated as algebraic quantities. We can add, subtract, multiply, and divide. However, both sides of equations must have the same dimensions. So, what is the only number you can multiply by and not change the value? The answer is 1. Any quantity multiplied by 1 is unchanged. To use a conversion factor such as 12 inches equals 1 foot, simply make a useful 1 and multiply by it. No, it doesn't come from the magic store, but it is useful like magic. The key to dealing with conversion factors is to realize that you're going to multiply by a number that doesn't really change the amount of what you have. Next comes the question of how do you make that useful 1? Well, there are two ways a 1 can be made using a particular conversion factor. Remember that any number divided by itself is 1. So 12 inches over 1 foot is equal to 1 foot over a foot, which is equal to 1. Or 12 inches over 12 inches equals 1, which is equal to 1 foot over 12 inches. Which one should you use? It depends on what you're trying to do. The unit you are trying to get rid of always goes on the bottom. Let's look at an example. How many seconds are there in one day? We will use the conversion factors. 1 day equals 24 hours, 1 hour equals 60 minutes, 1 minute equals 60 seconds. We'll set up the magic ones. 1 day times 24 hours per 1 day times 60 minutes per hour times 60 seconds per minute equals 86,400 seconds. Where are your useful ones? This technique can also be used to help convert from one set of units to another. Suppose you wish to compute the number of centimeters that would be equivalent to a length of 1 foot. From a conversion table, you find the equivalence 2.54 centimeters equals 1 inch, and you learned back in grade school that there are 12 inches in a foot. Using this knowledge, you proceed as follows. The foot in the numerator cancels the foot in the denominator, as does the inch in the numerator with the inch in the denominator, leaving the desired overall units of centimeters. The numerical values multiply and divide as usual to give the final numerical value of the answer. 30.5 centimeters is equal to 1 foot. Try this problem on your own. We'll examine Superman's gravity. In a fictitious set of units, 1 krypton equals 2.5 meters and 32 brainiacs equals 1 second. What is the 9.81 meter per second squared acceleration due to gravity expressed in the fictitious set of units? Solve this problem on your own and then click Continue. The answer is 9.18 meters per second squared times 1 krypton per 2.5 meters times 1 second per 32 brainiacs times 1 second per 32 brainiacs equals 0.0038 kryptons per brainiac squared. When units are not consistent, you may need to convert to appropriate ones. Units can be treated like algebraic quantities that can cancel each other out. See the inside of the front cover of your physics textbook for an extensive list of conversion factors to use when you are doing your homework conversions. This is similar to the table shown, but probably much more complete. You can also use the web to find most conversions too. Here are a couple more self-check problems that you can do. If you are only used to purchasing these items in a U.S. store and you travel to Europe, how would you know if you weren't getting ripped off from these companies? Can you determine if these advertised conversions are actually correct? Using dimensional analysis, do the exercise on your own and see if you can show that these packaging claims are actually correct. Does 37.5 square feet actually equal 3.48 square meters? How about the Scotch tape claim? Were you able to show that it is also true? Good luck! We will use two types of coordinate systems in physics. One is the Cartesian system, named after René Descartes, and the other is the plane polar system. They will be described in more detail in the following pages. You can make your own graphics that look like these if you want to, because they are very simple to create and they are common for all processes in physics. Another important idea to understand is the use of a proper coordinate system in physics problem solving. A Cartesian coordinate system is oftentimes used to describe the position of a point in space. We will use a standard XY coordinate plane with each problem set that we work on in this class. Left is negative and right is positive, just as up is positive and down is negative. Here is a Cartesian coordinate system, also known as a rectangular coordinate system. As you can see, the x and y axes are labeled and that there are several points that are labeled. Can you plot these points? -3, 4, 5, 3. The red dots are appearing at these points. Remember that you always list the x-coordinate first and then the y-coordinate when you plot an xy ordered pair on a Cartesian coordinate system. Additionally, the x-coordinate is always on the horizontal axis, while the y-coordinate is always on the vertical axis. You should, however, note that these are generic terms and don't always mean length versus length. Rather, they could be position versus time, or acceleration versus time, or even things like charge versus angle, or force versus distance. In any xy coordinate system pair, you really need to know what the units are associated with each of the axes, and make sure that you understand what the units on the graph represent about the information that is being plotted. Another way to represent information via a graph is to use the plane polar coordinate system. It is useful in different types of problems, especially in problems relating to rotational or vector-based analysis. Here you can see that the origin and reference line are noted by r, a vector length, and theta, an angle from our reference line. Notice that the distance r from the origin in the direction of the angle theta is counterclockwise from the reference line. This will be something we will consistently do. The point is labeled r theta. Let's agree again to the standard convention for labeling the parts of a right triangle. Let the right angle 90 degrees be labeled capital C and the hypotenuse lowercase c. Let capital A and capital B denote the other two angles, and lowercase a and lowercase b the sides opposite them, respectively. The Pythagorean theorem is about right triangles, that is, triangles, one of whose angles is a 90-degree angle. A right triangle is displayed in the diagram to the right. The right angle can be labeled capital C and the hypotenuse lowercase c, while capital A and B denote the other two angles, and lowercase a and b the sides opposite them, respectively, often called the legs of a right triangle. The Pythagorean theorem states that the square of the hypotenuse is the sum of the squares of the other two sides, that is, c squared equals a squared plus b squared. This theorem is useful to determine one of the three sides of a right triangle if you know the other two. For instance, if two legs are lowercase a equals 5 and lowercase b equals 12, then you could determine the hypotenuse lowercase c by squaring the lengths of the two legs, 25 and 144, adding the two squares together, 169, then taking the square root to get the value of lowercase c, namely 13. Likewise, if you know the hypotenuse and one leg, then you can determine the other. For instance, if the hypotenuse is lowercase c equals 41 and one leg is lowercase a equals 9, then you can determine the other leg lowercase b as follows. Square the hypotenuse and the first leg, 1681 and 81. Subtract the square of the first leg from the square of the hypotenuse, 1600. Then take the square root to get the value of the other leg b, namely 40.